So we're in the unit P packet on page 13, and I just got through saying on page 12 that these polar graphs take a lot of getting used to. So in theory, you've seen a lot of this stuff in pre-calc, but unfortunately, this is one of the first topics to get cut out of that course when people are running low on time. The first topic that gets cut out is conic sections, and the second one would be the polar coordinates and the parametrics. Right, so basically everything that we're reviewing in this Unit P packet, which is why I'm going into so much detail, because I don't have any faith whatsoever that this material was ever taught to you. Right, so yeah, that's disheartening, but it is what it is. So we're going to learn how to graph polar equations. Now, in some cases, it's really easy. Here it's saying r is equal to 3. Okay, r is equal to 3. That's wonderful. It's implied that r is equal to 3 for all theta. So for every theta, the r value is equal to 3. Now, you can make a table of values if you want, but that would kind of like be the same as making a table of values when you're graphing the line, well, y equals 2. So I'm going to make a table of values to say 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, negative 1, 2, negative 2, 2, negative 3, 2, negative 4, 2, and so on. That seems like a waste of time. So here I would be saying things like, all right, 3, comma 0, 3, comma pi over 12, 3, comma pi over 6, 3, comma pi over 4, and so on. You spend more time making the table of values than it would take to make the graph. So, but if you start plotting points, 1, 2, 3, all the way around, there are different ways in which you can plot these points. All right, and it has to do with the step. All right, in the old TI-84s, they had a function or a command in there where you could manipulate the step. How much space between each point before you connected with a line segment. All right, because the 84s, they didn't actually make smooth curves as much as they kind of fooled you using optical illusions into thinking they're making smooth curves by plotting the points so close together that it had the appearance of a smooth curve. All right. So what we're doing here is we're allowing for every single one of these values in between. We don't want to just plot at pi over 12 and say just connect the points, because if you did, you'd have straight line segments. It would look pretty angular. All right. I mean, it doesn't look angular when I do it because I'm a terrible artist. I mean, the word artist shouldn't even be used to describe anything remotely related to me. But, if we plot all these points in the intervals between the points that we plotted, then you'd get a more circular looking graph. All right. It's kind of part and parcel to that idea that an infinitely many-sided polygon is the definition of a circle. So you have two sides of a polygon. I'm sorry, two sides. Geez Louise. Three-sided polygon is your triangle. Four-sided polygon is your quadrilateral. Five-sided is your pentagon. Starting with five sides are your gons. Although an alternative name for a triangle is trigon, also a villain in the DC universe. But different conversation for a different day. Anyway, if you increase the number of sides, you're going to decrease the amount of space in between each vertex, and therefore end up, if you could get infinitely many sides in there, you would have infinitesimal space and therefore have a circle. Right? All of that is getting at the idea that we could just draw a circle. All right? Now, the big takeaway on this one is that, whoa, Nelly, r equals 3 to draw a circle? Not x squared plus y squared equals something? That's pretty awesome. Because if you think about it, That's pretty straightforward constant function, as opposed to, you try solving a circular equation in rectangular form, solving it for y, you get the plus or minus, the radical, it's a disaster. All right, so this is a nice simple representation of it's something that's fairly complicated in a rectangular coordinate system. Now for number 6, it's saying theta is equal to 3 pi over 4. That's for all, geez Louise, for all r. So no matter what r is, I'll just say n 3 pi over 4, where n belongs to the set of real numbers. That's allowing us to say, all right, we're going in one step in the direction of 3 pi over 4. Okay. So n is equal to 1. About 2, 3, 4, 5. Well, maybe we're going the other way. Maybe we're going -1, -2, -3, -4, -5. Maybe we're going pi, 1, 2, 3, and a little bit more. Pi steps in the direction of 3 pi over 4. All right, maybe we're going e. All right, maybe we're just going, 1.5, and everything in between. So what you end up with is a really simple way of writing the equation of a line. All right, now this is a particular type of line, a line that is a proportional relationship. If you're dealing with rectangular coordinates, it's just in the form of y equals, in this case, it would be nx or mx, but it would be the simple case where you don't have a vertical translation. All right, but we do want to be able to convert more complicated rectangular equations into polar form and polar equations into rectangular form. All right, we want to see, like the advantages of one as opposed to the other. Because if I'm a student in this class, I'd be thinking, all right, why are we learning this? What's the point? That would be number 1. Number 2, I'd be thinking, okay, note to self, easier to write the equation for a circle in polar form. What other equations are there that are easier to write in polar form? Which ones should I stay away from polar form for? Maybe a quadratic is a nightmare. Maybe a quadratic I want to stay in rectangular, but for an ellipse I want to go to polar form. These are some things I want to consider. All right, so that's where all this stuff comes into play. So we have all these relationships. I typed them up from the previous page, the most important ones. So all we need to do if we're going to rectangular form is we need to get rid of the r and theta and replace it with x and or y. All right. If there's a trig function, I recommend you try to get rid of that first. All right. Cosine. And you say, well, where's my cosine relationship? Well, it's right here, kind of. Cosine of theta is equal to x over r. Sine of theta is equal to y over r. All right, so 1/2 x over r is equal to r. Now, you might instinctively say, oh, I see an r, I'm going to replace it with the square root of x squared plus y squared. I recommend that you just kind of resist that urge, because an r is helpful, but an r squared would be even better. All right. And also, if you have a trig function, any trig function, it's going to have an r in it. So if you have a standalone r and then another trig function, there's a hidden r that can be combined. Like in this case, if I multiply both sides by r, cancels on the right, combines on the left to an r squared, I have 1/2 x. Now I can do a quick substitution replacing the r squared with x squared plus y squared. So what I'm going to do is get everything over to the same side. Going to leave a little space to complete the square. I'm going to use a good old formula b squared over 4a to allow me to complete the square. So my b value is negative 1/2, so it's going to make 1/4 over 4 times 1. So 1/4 divided by 4 is the same as 1/4 times 1/4, which is 1/16. So that's what I'm going to tack onto both sides. All right. So we're looking at x minus 1/4 as a quantity squared plus y squared is equal to 1/16. All right. So that's going to give us a circle with a center at 1/4, 0, and a radius equal to 1/4. And now if we look at the structure of the polar equation, we're looking at a few different things, but the obvious thing would be that 1/2. That 1/2 actually represents the diameter of a circle. You know, if your polar equation is in this form, that would be the diameter of the circle. Half of a diameter is a radius, so half of a half is 1/4. Right? Anything in the form of r equals a cosine of theta would be a circle that is symmetric about the x-axis. Right? And so we can, get a lot from the polar equation that, maybe you kind of look at it and say, well, it seems like it would be unnecessary to put it into rectangular form. And, this first time it wasn't unnecessary because we needed to deliver that information through the learning process, or use the learning process to deliver that information, I should say. But now that we have that information, I think it would make more sense to rely on the polar form. So if I go to my Desmos calculator, I can put it in polar form by hitting that little wrench. Type in r equals 1/2 cosine of theta. And you just got to type in the word theta and it converts it over. And you can see that I typed it in incorrectly. Yeah, you can see that would be the equation for a straight line. Cosine, gotta hit the right arrow to get out of the fraction tool. Right, there we go. A little bit better. It's like, well, that's not any better. Well, yeah, well, you gotta zoom in a little bit. All right, so that would be your circle. All right, so, well, inadvertently we learned what the structure is for a vertical line in polar form. Let's see in the next example what happens in terms of the center. All right, so I'm going to rewrite, well, I was going to say rewrite it, but I'll rewrite it up here as -5 sine of theta. But I do want to keep it in this form for my substitution. 5 y over r is what sine is equal to. I'm going to multiply everything by r. So r squared plus 5y is equal to 0. X squared plus y squared plus 5y. I'll leave a space to complete the square. We do that b squared over 4a. So I'm adding 25 over 4 to both sides. All right, so we're looking at x squared plus y plus 5 over 2 squared equals 5 over 2. All right, so from this we get, well, Oh, sorry. I wrote 5 over 2 for some reason. Oh, that was interesting. 25 over 4. So for this one, we would get a radius equal to 5/2. The center would be 0, comma, negative 5/2. So it does appear that there's a relationship between the center and the radius in both cases. All right. But specifically, and I'll shrink this down a little bit so you can see. And actually, it's really weird. I must be off my game. I did the same thing over here. This should be a 1/16. I was wondering why my relationship didn't work out. Huh. Anything taken out of context. Right, yeah, so that should have been with a radius of 1/4. So, center, negative 1/4, comma, 0, with a radius of 1/16. 1/4. Jeez. It's like I'm trying to botch this. So anyway, we'll take a look at the graphs. Now you say, well, this is rectangular form. Well, not for long. I'm going to put it in polar form. R equals, I'll write it as 0.5, cosine, just type in the word theta, 0 to pi maybe, but typically we want to go 0 to 2 pi as a domain. And you say, well, I don't see anything there. This doesn't work. Well, look at the scale here. It's going out to 50 for crying out loud. I hit the home button, so it brings it in a little bit closer. And now if I go even closer, I can see a little bit of a better view. So I think it's pretty clear, hopefully you agree, that in number 7, the coefficient corresponds to the diameter. All right. The cosine corresponds, well, it doesn't really correspond, but it indicates x-axis symmetry, or a polar axis symmetry. All right. Now we can do the same sort of thing, but this time with the negative 5 sine of theta. That's not what I wanted. So the diameter is consistent with the coefficient because the radius is 5/2, 2.5, all right, and it does seem to be symmetric about the y-axis, all right. The only difference is because it's negative, it's the negative y-axis as opposed to the positive y-axis. The coefficient of the cosine was positive, so it was on the positive part of the polar axis, positive x-axis, as opposed to the negative x-axis. All right, so a lot of little relationships that come from this that make it pretty easy to kind of go from one form to the other without having to do all this work. All right, so then number 9, a little bit of a different story. We have r minus r times, we'll make it y over r. So r minus y equals 0. Now that r can be thought of as the square root of x squared plus y squared minus y equals 0. I can add the y to both sides for the purpose of squaring. So we get x squared plus y squared equals y squared. So it looks like we have a common y squared that's going to cancel out, and we get x squared equals 0, and you get x equals 0. All right, so let's take a look and see if that actually ends up being the case. So r minus r sine of theta equals 0. Equals 0. And again, 0 to the 2 pi. Enter. All right. So we don't see anything there, but that's not 100% surprising to me, because x equals 0 is a vertical line. So there's a couple of things that could be going on. One, it just could be overlaying with the y-axis, so it's just not visible. The other thing is Desmos just might have a problem graphing vertical lines in polar coordinates. I didn't think it did, but you never know. So what I'll do is I'll just turn off the y-axis here and see what the story is. And it's still not showing up, but it should. So let me get some more domain. All right, so we found the exception that proves the rule, I guess. That tends to happen sometimes, but I wasn't expecting it to happen here. All right. It is what it is. All right. Another way of handling this, would be to factor out an r and get a 1 minus sine of theta. Set each factor equal to 0, thinking of it as a quadratic. R equals 0. Well, that's just a pole. That doesn't count for anything. It's a circle with no radius. It's non-existent. All right. In rectangular coordinate system, if you got something like x equals 0, that was a location. Here it's a size. All right. If the size is equal to 0, then the object doesn't exist. Then we can solve this equation where we get sine of theta is equal to 1, and that happens when theta is equal to pi over 2. All right. So either way, we would be getting that vertical line in rectangular form. All right. So the fact that it's not showing up on Desmos is weird, but that's okay. All right. Now, if we want to go the other way, this is a little bit easier. We just have to rely on x equals r cosine theta. Y is equal to r sine theta. All right. However, I don't know that I necessarily want to go plugging stuff in and then distribute. I think it's easier to distribute algebraically first, see what's going on, and then go from there. So x squared minus 8x plus 16 plus y squared equals 16. Okay, so you see you have a common 16 here, cancels out to 0. All right. Now if I reorganize, I get x squared plus y squared minus 8x equals 0. X squared plus y squared is equal to r squared minus 8x equals 0. If our goal is to get it into rectangular, polar form, I would just need to swap out the x for an r cosine theta. But again, I have that common r, which doesn't amount to anything, because if I set that equal to 0, again, it's a size relationship. It's not a location, it's a size. So a circle radius of 0 doesn't exist. So the only relevant part of this would be r is equal to 8 cosine of theta. All right, now what we learned back in numbers 7 and 8 is that if it's a cosine equation, it's going to be symmetric about the positive, and so it's a positive coefficient. So positive x-axis, it's going to have a diameter of 8, with one end of the diameter being the origin. So its center should be at 4, 0, which corresponds with the equation that they gave us. So we're in good shape here. All right. And so the last one on this page is number 11. We have x squared over 4 minus y squared is equal to 1. That's a hyperbola. I'm going to do some housekeeping first. All right. So I would multiply through with a 4 just to clean things up. Now, the level of cleanliness is dependent on, whatever you're comfortable with. If I can get rid of the fractions, I prefer to do that. All right. Now, in this case, it does not look like we have the ability to utilize the r squared is equal to x squared plus y squared. I mean, there is a way around it. It's just not always worth it. So I'll show you, and then I'll show you what you're going to end up having to do in most cases. All right, so there's a little trick here, and that is to say, if I want this to become x squared, I should turn on my pen, x squared plus y squared, then I can do x squared plus y squared minus 5y squared is equal to 4. And that's because y squared, 1y squared minus 5y squared is 4y squared. That allows us to make an r squared, and then we can make this minus 5, and then instead of y being r sine theta, it's y squared, so it would be r sine theta as a quantity squared is equal to 4. All right, which becomes r squared minus 5r squared sine squared theta is equal to 4. Now at this point, you can GCF out the r squared. 1 minus 5 sine squared is equal to 4. And then from there, we can just divide, and we'll have we'll have a relation that's solved for r in terms of theta. All right, we'll just have to take the square root. So that's one way to do it. But the thing is that that method doesn't always pan out. Because you get the r squared part of it, but then usually, well, not, I don't want to say usually, but oftentimes, the remaining part of the expression is not any better than what you started with. All right, so we could do this. We could take the root of both sides. And so we'd be looking at r is equal to plus or minus 2 over. Nothing wrong with having a radical in the bottom of a fraction. Whoever told you that was not allowed was a liar. So 1 minus 5 sine squared theta. So that's one way of representing your answer. All right. The other way, or I'm sorry, solution, because in theory both solutions should lead to the same, if not similar, answers. So the other way would be to go off of this. And immediately replace your x squared with an r cosine theta squared minus 4r sine theta squared is equal to 4, and then square it out from there. right? And you see it's kind of shaping up the same way anyhow, except you'll have a cosine in it instead of consolidated in the form of sine. So I'd factor out an r squared. And you'd say r squared is equal to 4 over, and you might look at this and say, but it's a different answer. And I say, well, yeah, but cosine squared is 1 minus sine squared. So if you make that substitution and combine it, you get the same answer. All right, so, but you don't need to, so don't. All right, so in terms of steps, it looks like it's about the same amount. I mean, maybe you save yourself half a step by doing it the other way. I don't know, but it just strikes me as the kind of thing where it's really not worth the effort. You know, make the substitution immediately and just go from there. That's what I would do. Yeah. If you know what, I'm giving up on that line draw tool. I'll tell you that. All right. So either way, so big old or.